Okay. So we'll start off slow because more people are coming in, I hope. Well, everyone, this is our last chance to globalize together and be globalized. So I am looking forward to it. We have a lot of things to do. Thank you, Derwin and Jennifer. Um, So I am still admitting people as we talk. So I'm kind of watching and clicking, and then I'll come back to it. Um, but it may not be the very last chance to go ahead and be localized. So we are going to concentrate in a couple minutes on passing this ARRT exam. But then, as a lot of you might know, I do CAT scan and MRI uh, as well on the side. You got to pass this registry first before you entertain any other options. But let me go ahead and share my screen for a second. And I'm going to go ahead and show you a couple of things. Okay, so if you do decide to or have interest in learning about CT or MRI, of course, first choice is the bachelor's degree, which is nice because you get a degree, you get a bachelor's degree. And you also, if you take MR or CT, you kind of knock out one of those registries, comes with all the clinic you need and everything else. But if you want to do something a little bit faster, you can take a 7/8 week online twice a week, 6 to around 8:30 class with me and my colleague, Mr. Frank Cairo. He does all the anatomy, safety protocols, that kind of thing for CT and MR, and I do the physicsy stuff. So you can uh, get more information by going to their website. I'm going to put everything in the chat. Where's my chat? Chat. Um, yeah, it's more like 7 or 8 weeks. I actually have 7 classes for MRI and I have 4 classes for CT. So CT is a little bit shorter, but that is some information. And whoops. And here is some more information. You can, just copy and paste these someplace where you'll have it. You can also reach out to me, but you might want to use your personal email because I don't know how long your City Tech email will last. So if you want any information, just get in touch with me. We provide clinical or the classroom stuff, the mandatory 16 hours, or both. So you can do one or the other or both. So just let me know. Okay, that said, what I wanted to do is quickly give you some information. I'm going to give you some links. So if you guys remember the Photon Interaction, that was always a good site. So let me go ahead and I'll have 3 more people to admit. But let me go ahead and anyone with the link, copy the link. Go back to the chat. Okay, so this is the interactions. So that's there. And then meeting controls. Okay, so this is a separate presentation just on quality control and equipment. It's something I've had for a little while. Could be useful. So why not send it to you? It's my theory. So the link for that is coming. Okay. So this right now is the link to some quality control stuff. And then I did update this particular presentation on digital imaging. It's mostly DR. So guys, you need to know CR and DR. You're the last class to know it. So we'll go over that in just a second, but let me go ahead and share this one because it might not be on the original link to the Silidar, which I never took off. So you should have access to a bunch of my videos. So here is the updated link to this particular lecture. Then I have a small little table that might be helpful. So let me go ahead and share this one. Copy the link. So there's yet another one. And maybe the most important one is today's lecture. So here is the link to what we are doing today. Let me copy it. Okay, copy that. So 2026 image eval review. Okay, that's that. Okay, I think we are ready to start. Let me see, is everyone here? I have 52 people, so there's a couple people missing. A few people missing. Okay, you're welcome, son. All right, so you've already done your ethics requirements and filled out your application, so that's good. What I want to point out now is this is the task inventory that is related to your exam. So it's not the content specs, but it's something you should definitely look at if you have not read this. Okay, it's only like 2 or 3 pages of information. And it tells you what's on there in addition to the content specs. So a little bit more information. Let me go ahead and copy this or share it. Share the file? No, I don't want to. Oh, wait, there is a web copy button. Okay, let me copy that and put that in the chat. So this is the task inventory. Give me 1 second. Oh, okay. Here it is. Task ASRT task inventory. Abbreviate that. All right, you can try that out. And last but not least, the one everyone should look at is the actual content specs, okay, that we're going to go over just a little bit. So a few more people coming in or re-coming in. So this here, share this, super important. Okay. Yeah, I'm going to keep checking the waiting room here and there. Let me just get the content specs. All right, those are the content specs. So I could stop for a second here and say hi to everyone. Okay, so first of all, it was a pleasure. I thank you for all being great over the last couple years. I thought you were a really good class, and I've gone through 20 of them at least. So I really enjoyed going on the walk with you guys. For those of you that did the Making Strides walk in Coney Island, I've actually never gone before, and now I plan on trying to always go. So that was a lot of fun. This is being transcribed, apparently, fine with me. So I enjoyed it. I hope you did too. So let's get to business here. I'm going to share again, and I'm going to go back to the content specs because I want to share with you a little study technique. So as a lot of you know, we don't teach for the test, right? We use the ASRT curriculum, but now it is crunch time. And I have a study technique that is, designed to, you got to put some work into it, but it's designed to get you to pass this test as well as the CT and MR, different information. So what I think is worthwhile at this point is to study based on questions. So whether it's Clover Learning or boot camp or wherever you're getting your questions from, SEA, that yellow book, what you want to do is analyze questions. When you get them correct, you want to make sure why you got them correct. Now, when you get a question wrong, you want to ask yourself, are they asking a lot of questions on this topic? That's where the content specs come into play. And if they fall into, let's say, procedures, well, then you need to focus a lot on it. Patient care, not as much, about half, okay? But what you can also do, besides looking at these broad categories, is you can scroll down and you can literally use this stuff information here as a checkoff, right? You need to know a little something about everything in this content spec. I know it's a lot, but this is what we've been preparing for 2 years, right? So there's a lot of information there. Now, when you get a question wrong, you want to review the answer, but then you want to go another step beyond that. What I would recommend is looking at all the other choices, all what they call distractors. So if the answer is A, and you kind of understand why it's A, you want to ask the question, why was B, C, and D incorrect? Because a lot of times those choices will be correct in another format, in another type of question. So you want to know what the wrong answers mean, right? And if there's a choice that you don't understand, even though it wasn't the correct answer for that particular question, you still want to know what it means, right? And you're going to do that for tons and tons of questions until your self-score keeps improving and improving and improving. What I think you don't want to do, and I know people are tempted, take one book at a time, starting with the first page and turn and turn and turn and turn. I don't think that's a good idea. I think you should focus on the questions you're getting incorrect. That way you know what your strengths and your weaknesses are and how they relate to what's definitively on the test. Here's something else that you should do on test day. On test day, when you get in there, so first of all, you should make sure where you're going for your test and, make sure you know where the parking is, even if you have to take a day before sometime, just to make sure you know where the test center is and all of that. Definitely eat breakfast. Okay, so you get there, and a lot of people say, well, you get that whiteboard, so you should go ahead and write down everything you remember. And this is true. You should do that, right, Aya? You should do that, except you can practice that at home. So my suggestion is take a blank paper, write down everything you know, and then see how you did. Did you forget some things? Did you forget some formulas, right? And then do it again. Do it a few times, maybe over a few days, so you get good at that. So when you walk in and it's time to write down everything you remember, you already put a lot of information and work into that happening, right? So I think that will be helpful for you as well. While you're studying, every question has a twist to it or a catch, right? You want to get good at figuring out what they are trying to ask. And as I've said to many people before, you should look into what that catch is and try to kind of figure it out. So if you see it again, you recognize it. Flag questions that you're not sure about it and move on, right? You will have, so if you guys have not looked at this closely, okay, you'll notice down here that there are 30 unscored pilot questions. So if you have a question that doesn't make sense, don't let it throw you off your game or depress you or make you go downhill, right? It may be one of those questions that are unmarked. They're just using it for research purposes. It may never make it to another registry again, right? If everyone gets a question wrong, it's too hard. If everyone gets a question right, maybe it's too easy and they don't use that one either. So you don't know which questions these are, so you still have to answer everything to the best of your ability. However, that's what I think you should not let it psychologically affect you. Okay, now don't leave any questions blank, right? And so shout out to the person who knows who they are. I'm not so sure anymore about changing your answer. Generally in class, I've always told people to not change their answer, but there's been some research, I haven't really looked into it exactly, that says, well, maybe you should change your answer. And people that change their answer, generally 70% of it change it to the correct answer. So I don't know how I feel about that. I'm in the middle of that. I still see personally lots of people changing their answer to the wrong answer. But then again, I don't see the people that change their answer to the correct answer, right? If you change it to the correct answer, it just gets marked correct. And I don't know. So you have to kind of think about it, for yourselves about who, is doing that and see if it's best for you. My advice is flag it. At times, other questions can help answer other questions, right? And on your, whiteboard, if you find out something that is the wrong choice but rings a bell with something, definitely, jot down a note. You're allowed to take notes. And I think the test is like 3 or 4 hours long. So I think most people will have time to take the test and watch for things. Let me see. I'm trying to get my chat back here. Can I let someone?
Crystal's trying to get in.
Yeah. It's too late. No, hold on. Where am I? Let me stop sharing for a second because I can't. I have my little laptop and it's like hard to see everything. It looks like everyone's in. Oh, maybe not. Hold on. I think she's in. All right, she's in. Okay. So, any questions before we get started? If you have any questions, email me and let me know. All right.
Professor,
So, yes.
regarding the formulas, you said that, we could write it down on the whiteboards. I can't recall who said that normally they give us the formulas. It's just that we need to know which formulas to use they normally give us the formulas written down or something like that.
That could be the case. That would be really nice if they give you all the formulas.
Somebody said that yesterday.
I will double check that. But that would be news to me, and no one has ever brought that up to me before until just now.
Where did I hear that? Yesterday, I think.
We'll check, but don't bank on that until I verify that. Make sure you know it. And as it is with all the math, always remember that just because your answer appears, it could be the wrong choice, right? Remember, I've told you many times, I will do all the calculations purposely incorrect, right? I'll not square something. I'll not reduce something. I'll have a decimal point in the wrong place. And that's, something that they will do. So just make sure that all your math is correct. Just because like a number pops up immediately, don't automatically assume that's the right answer, right? Because it may not be. Of course, I will eventually send you this recording to your City Tech account because those are the ones I have. So let me go ahead and get my presentation back up. Okay. You guys are all going to do fine. Don't try to cram either, right? Like the night before, watch your TV show, that you're used to watching, Chicago Fire or whatever you guys are watching. And again, make sure you have breakfast. It's good to have a little in you. Some people are going to be like, I can't eat, um, but you don't want to go in. It's a long exam.
Hi, Professor.
And besides the mock registries that we do, yeah, I'll get to you in just 1 second. That was Richard, right? Before, see, I forgot where I was. Okay, maybe I'll remember. Was that you, Richard? Did you have a question?
Yeah, I had a thought. Yesterday I was going through Rad Review. So there was a question I was trying to check, and then usually I normally study with the textbook, and then that made me start questioning. So I think the reading from the study format you gave us is the best. You go through the questions, and then you now start questioning why the answers are wrong or why they're right. So that really helped me. So I discovered that was a good one. Thank you.
You're welcome. Yeah, it takes a little bit of time to do this. Oh, now I remember what I was going to say. Make sure you do a few mock registries and time yourself. It's nice to, do a few questions each day, but you do want to make sure that your stamina is good enough to take a long test, right? Now I know you had mock registries because that's built into college, but if you can take a couple more and see how long things take and how you do. I think that'll make you feel more comfortable. All right, you guys ready? Here we go. So what I did for this presentation and what I will have to change for next year. So by the way, if you guys do not take the registry for a long time, it is going to change in March of next year. But I would suggest not waiting, right? No one's going to wait that long to take the registry. Okay. So I have taken the current specs and I've put them here. And what I've done throughout the presentation is label my questions or slides with information. So you might be able to find things a little bit easier and do Control F to find information, that kind of thing. Okay. So because I am recording this, I get to talk as fast as I want. Okay. You guys ready? All right. We're going to start at the very beginning. We're not going to spend too much time on things that are super easy like this. Mass, milliampere seconds, right? This is where your current heats up. Remember, thermionic emission is probably on the registry somewhere. I mean, if that term is not there, I'll give you guys money. I'm sure it's there somewhere. All right. What is mass? It's the product. So MA times time, milliampere seconds. MA goes up, intensity goes up. Remember, intensity is how much radiation you create. If time goes up, simply you keep burning off thermionically electrons, then your intensity amount of radiation will go on. More electrons, eventually more photons. Right? Pretty easy concept. You want to reduce the time and increase the MA if you're worried about motion, right? So as long as you have the mass that you know will work for you, by the way, that's the reciprocity law, right? Any combination of MA and time that gives you the same mass is the same intensity, right? So basically, we spelled out everything here. It's directly proportional. So if you double the MA, you are approximately doubling the amount of radiation, what we call the intensity. Nothing really new here. Okay. Compared to screen film environment, mass no longer controls what we used to call density. It's now all about making sure we have a minimum exposure to penetrate the part, right? Remember our very first labs in image eval, you can't make up for a lack of quantity, a lack of intensity with super high KV, right? If you have a few super strong photons, that's not enough, right? You need a significant amount of intensity. But you also need, you can't make up with intensity either. So if you have a lot of photons, but they're all really weak, low KV, long wavelength, then you will not penetrate. And it doesn't matter if you have a tremendous amount of them, right? So we have to have that balance. Don't forget that. So again, reciprocity law means any combination of MA and time that gives you the same mass will give you the same exposure. One of the big things we have to worry about, again, is if we don't have enough photons, right? And that's sometimes known as photon flux. So if we don't have enough photon flux, then it doesn't matter if what you do have is very strong. Remember, most of the radiation gets stuck in the patient, which is unfortunate. So we're only talking about 2% of radiation that makes it into what we call the remnant beam, right? You have the primary beam prior to hitting the patient, and whatever makes it out is called the remnant beam. So KV is that potential difference. It's the push, right? We can create all of these electrons, but if we don't put thousands of volts into them, so we think of 48 kV as being a really low amount, but it's still 48,000 volts if you think about it. So we need enough kV to penetrate the part. We need a certain amount of kV to create some of our intensity, right? So remember, intensity is created by increasing MA, increasing time, but also if we increase kV, we get more interactions, right? We get more Compton/photoelectric interactions. So kV is considered a quality factor, but it affects intensity, and it also affects the hardness of the beam, right? So if you increase kV or you add filtration, the beam will be harder, right? As they say. So remember, 15% rule kind of works into this. If you go up approximately 15% in kV, that will double your intensity. Let's keep it going. So if we don't use enough kV, like I said before, you get what's called quantum model. That's a lack of photon flux. In terms of the detectors, they are starved, right? We're not feeding them enough. So photon starvation is another term. And it results in a grainy image. And this is really what everyone is afraid of, because when you use too much radiation, we all know that everything gets fixed and looks great. The problem is when we don't have enough radiation, we don't get enough intensity, it results in noise, and it's pretty hard to fix noise, right? So that ends up being a repeat. Now, what happens when we increase kV? So generally speaking, increasing kV is good, right? It means you will penetrate more. Maybe you'll improve that 2% to 2.01. You know, it's a small increase, but you get a little bit more photon flux. The detectors get a little bit more radiation. Do you increase scatter? Yes, but the increase in most of the techniques going from screen film to digital, whether it's CR or DR, is worth the effort, right? I've always talked about the hand. I used to use like 52 and 304 mass. Now everyone is using 62 or even higher at like half the mass. So we like KV. We shouldn't worry about creating too much scatter. Right.
Hi, Professor. You said increase in the KV, but it has to be by a certain amount for you to actually see those changes. It's like, what is it, 15%? You say increase the KV.
Yeah, I think maybe it's 4 kV to make a noticeable difference.
Different, yeah. But I mean, if you want,
yeah. Yeah, if you change from like 80 to 82, that doesn't really do anything.
Right. And to to cut the patient dose, wouldn't it have to be like 15% in order to half the patient dose, something like that?
Well, I mean, it could be, but you know, if you did 7%, that would be a 25% difference in dose
Okay.
instead of 50%. So
Okay.
you can, you know, that's just the 15% rule is just a nice rule to have in your head to understand the concept. But you know, you don't have to literally cut the mass in half and go up in 15%. You can go up 7% or 7.5%.
So you said
Instead
a
of
noticeable
15%.
difference is about four
I
percent.
think it has to be at least 4 kV,
Okay.
if I remember.
Okay.
So yeah, like I said, 15% is the rule, but you don't have to always use 15%. You can, I mean, if you think you need a lot more, right, you can use 15% rule twice. I had a question like that on one of my tests that a bunch of people got wrong. You had to apply the 15% rule twice. I think I remember talking to you, Dave. Okay, so on average, though, 15% increase in kV will double your intensity. Okay, so some geographical stuff, right? So OID, we know, is the measurement of the object to the image receptor. What do we want to remember about it? It affects magnification. The more OID, the more magnification. So we always want to reduce our OID. Also, if you have more OID, more photons will die because they'll have that space before they ever make it to the image receptor. So sometimes we've used OID instead of a grid, right? But the problem is things get magnified. So with a grid, you don't magnify the image, you just help get rid of scatter. But increased OID will also do that for you. So that's that air gap technique that I just mentioned. Generally speaking, we're not really using this because of the magnification. We also have new algorithms, but they probably haven't made it to the content specs. So some of the newest things you'll see will not be on the registry because the registry only changes every 5 years, right? Based on surveys. So what that means is, let me just check my chat here. Oh, someone is here. Okay. So what will happen is, let me stop for a second. Let's see who's here. Participants. How come people are back? I think maybe once I let someone in the first time, they're in the second time. I don't know. But thanks, guys. Yeah, I don't see anyone in the waiting. Am I wrong?
I think
All right,
Amy
well,
has a question.
Yeah, oh, okay. What is your question?
So I never really thought of it. You were at the air gap slide. I know air gap is
Mhm.
used as like a grid. Do we also increase the technique? We do, right? If you use air gap?
You do not.
Do not? Okay, great. Thanks.
Um,
Well, Professor,
you
go ahead, sir.
yes. Let me think about that for a second. You shouldn't it
Let me Google it too,
maybe
actually.
maybe a little bit, but not nearly as much as you would with a grid, right? And
Copy.
the SID, right, which is the one we're up to right now. The SID is still the same, right? When you change your OID, that is happening within the SID, right? If you have 72 inches, right, and the person is against the image receptor, and all you do is move them back a certain number of inches, you still have 72 inches. So I don't think you need to change your technique very much. And if you do, I'm not sure how much. I got to double check on that kind of stuff. So Catherine, take notes.
Professor,
That's one I have to double check. Yes.
Yeah, so if you increase the OID, like 50, how much inches from the image receptor, wouldn't that also increase the patient dose because they are closer to the primary beam? Wouldn't more than if they were farther away, like 72, and they are closer, wouldn't that increase the patient dose?
Uh, it's hard to say. It might increase the dose, but also it will increase penetration. So
Yeah.
more photons will go through at the same time. But yeah, dose goes up when SID goes down. So if you bring them closer to the tube, they should get more dose, right? Because the photons haven't had a chance, as many of them at least, to die in the air.
Right.
Right. Also, try not to read into the registry questions too much and try not to pretend what you would do to correct the situation. Just answer the question, right? Don't read into it and say, well, and think in your head, I would raise the SID or I would do something. Also, a lot of the questions are theoretical, or at least a few, where it sounds funny, but assume sometimes what the answer may be, regardless of whether there's actually a patient on the table or not, right? You might think to yourself, well, you're never going to take an x-ray without a patient. And that's true. But for the exam, sometimes you have to think about what's happening regardless of whether there's a patient on the table or not. Okay, let's keep going. I don't see anyone trying to get in. Okay. So SID is from the image receptor to the tube. By the way, it's not the tube housing. It's the circular part of the tube, right? Which is why when you measure, it always starts at 10 inches or something, right? It always accounts for the collimator box itself. So if you increase your SID, right, less photons will hit the image receptor. This is governed by the inverse square law, which has been, built into you guys. You should be happy if you have like 10 inverse square law questions, right? Because if you know them, then you know them, right? So here it is, right? We know that when you half the SID, you will quadruple the intensity. Direct square law is the one I always found a little bit more important because we're generally not looking at the amount of radiation, but we are looking to change our techniques when our distance changes. So if for some reason you have a technique, so you have 20 mass, but now you cut the distance in half from where that 20 mass used to work, we now know that it is going to go up 4 times. And in terms of your technique, you should use 1/4 of your technique. So if you started with 20 mass at 72, you go to 36 inches and half of 72. We should go from 20 mass to 5 mass, right? Now, if you get a question that is directly where the SID either doubles or halves, then you don't have to do the math, right? You could do what I just did in your head. But if you go from 36 inches to 32 inches, then you have to plug in everything. Just don't forget to square. And as I said earlier, make sure that your answer is correct. You're going to get an inverse square law question. It's like one of the golden rules, at least one, if not more than one. Okay. Didn't we do this? Oh, yes. What other things are going on with SID? So in a perfect world, an increase in SID will reduce blur, so that'll reduce distortion, right? Very hard to see in reality, right? We were all counting line pairs, if you remember, to hopefully see better spatial resolution with increased SID. But technically for the test, right, you want your SID up and your OID down. Those are better for distortion and for magnification. focal spot size. So again, kind of hard to tell, right? We tried this in the lab. It's true though. It worked out for us in the lab, but it's kind of something that you probably wouldn't notice on an actual radiograph because you're not taking x-rays of line pair test tubes. However, right, you should know smaller focal spot, better spatial resolution, better sharpness. Line focus principle just says that as the x-ray, do I have a picture of this? Maybe not. Line focus principle is the cathode ray. By the way, cathode ray is the stream of electrons coming from cathode to anode, comes in, and when it hits the anode, it narrows down, right? It narrows down such that it makes the photons that are coming out of the tube more streamlined, right? So that's going to give you less blur, less penumbra. They're going to diverge less to begin with. Remember, the main issue with focal spot size is why can't we just always use the smallest focal spot if it gives us the better spatial resolution? Is that sometimes the objects are too big and you risk breaking that filament if you're trying to, go through a pelvis and you need that thermionic emission to keep going for a little bit longer, or you have your MA higher, meaning you're heating up the filament. So unfortunately for bigger objects, most objects that are done in the bucket, so hip, femur, spine, shoulder, skull, those are all going to use the large focal spot for the most part, right? Because you risk literally destroying the small focal spot, which remember is linked to, it's all about the filament in the cathode, right? The longer filament goes with the larger focal spot, for example. The effective focal spot always smaller than the actual focal spot. The actual focal spot is literally the part of the anode that gets hit by your electrons. Once it gets narrowed down because of that angle, right? Remember, the anode has an angle that helps reduce the width of your photons going down through the patient. Where they hit on the image receptor is technically your effective focal spot, even though it in a way doesn't really exist. Don't get too caught up on that. Just remember, actual focal spot is always larger than the effective focal spot. Okay. Let's see if there's something we didn't go over here. Yes, smaller focal spot gives you less blur. We call that penumbra. Again, this can be referred as increased spatial resolution. Yeah, whenever blur goes down, spatial resolution increases. All right. Absorption penumbra. And I've added some notes like this portion up here to kind of give you exactly what you need to know. I don't think those are on the original slides, like this one. If you have basically an angle of the object that matches the divergence of the beam, that is going to give you the least penumbra. It's going to have the best spatial resolution. Whereas some spherical object that does not match up well, gives you a very shallow slope, is going to give you the least spatial resolution. In other words, it will have the most distortion. Will you get a question on this? I don't know. Will you get 10 questions on this? Definitely not. Right? Maybe one question. Okay. Here is the penumbra formula, right? You have to go over all of these formulas, right? If you see that your math is not great, then you have to study that more than other things, right? This is what I mean by kind of unequal studying. Don't give the same amount of time to stuff that you're pretty good at and get the answers correct. So how do you know which questions you get right and which questions you get wrong? You take more questions and you analyze them, right? You can even put that stuff into AI, right? Copy and paste it into, ChatGPT or Anthropic or whatever, and just say, give me the categories where I'm getting these questions incorrect. And then it'll tell you, well, you're getting all these right, you're getting this percentage right, you're getting this percentage wrong. Well, you got to study the ones that you're getting wrong, right? Unless they hardly ask any questions on that topic. That's what I was saying before, right? I'm not saying you shouldn't study, but if they don't ask a lot of those kind of questions, then you don't need to put as much time and effort into it, right? And also, again, if you flip any of these variables, you get the wrong answer, but that shows up as one of the choices, right? That's the easiest way to make up test questions. Just flip things around. So again, be careful when you get an answer immediately that matches one of the answers. Don't be so fast to pick it. Just because it's in front of you might actually be the wrong answer. Grids. So we all know grids are going away, but they're still on the test. And they're still on the content specs for the next 5 years, right? That's what I mean by, if they don't change it for this, coming March, the next time things could be removed is, another 5 years. So there's going to be old stuff on there. For example, I know this is not part of the registry review really, but image intensifier too. You need to know that, right? But so many places are using flat panel detectors now, but they still didn't take that off for some reason. So the next time that would be over is 5 years from 2027, so to 2032, maybe it'll go off. So grids, what are they? They clean up scatter by killing photons that are diverging at wrong angles, where they didn't pick up good absorption information about the tissues that they travel through. So they're kind of carrying misinformation, and that shows up as noise or a graininess. So grids, having lines that will absorb those photons that come out of the patient, right? So they're not going to affect anything that's photoelectric that gets absorbed by the patient. They're only going to be dealing with Compton scatter. So Compton scatter, if you remember, is not good for the patient because you have an ionization there. But what's worse is it could affect the image because the photon changes direction and comes out at a weird angle, maybe absorbing other information from other tissues that don't make sense, right? And if that happens to one photon, it's no big deal. It's when it happens to millions of photons within one exposure that you could potentially see that as noise. So how do you clean that up? Well, before you get to the image receptor, this errant photon will hit a grid line and get annihilated. As we know, the problems with grids is they're so good at what they do that, even a slight angle that has mostly good information in it can be absorbed. So the golden rule is we have to go up approximately 4 times in our intensity. So we can quadruple the mass. Usually we work with mass, right, then versus kV, because you will get a little bit more scatter when you increase kV. So it doesn't make sense to increase your technique with kV, which will only give you more scatter. It makes more sense to increase your mass when you're dealing with a grid. And what will this do? It'll get rid of some of the scatter. So noise will go down. When noise goes down, contrast goes up. So always in your head, think about what's happening to noise. If noise goes down for any reason, contrast will go up. So we know that we can break down grids. They're not all exactly the same. Some of them are parallel, where the lines are all parallel to each other. Some of them, the lines are cantered, which is a term for angle, cantered in such a way that they match with the divergence of the beam. That's why they have certain focal distances that you can use them within, right? They may all they may give you some of this stuff that no one thinks about. You're not worried about this stuff in clinic so much, right? Because everything is purchased to work correctly, right? Remember, the school and the registry people are not thinking that something might not happen because the department has already purchased something that makes sense. They're thinking about everything from a theoretical kind of standpoint. All right, so the space between each lead line, that interspace, is known as your grid ratio. It's based on the height divided by the distance. When you increase the grid ratio, the lines come closer together. So when you increase the grid ratio, it makes it easier to kill photons because the lines coming closer means that they have more of a chance of getting annihilated. So using a high grid ratio is something you should not do if you have a lot of angulization in your projection, right? Or you're doing portables where there's a lot of angles. Right? You want a lower grid ratio, right? A lower grid ratio. Hold on, a couple people just came. Okay, a lower grid ratio gives you better latitude. Latitude is our margin of error. So most X-ray rooms have something like a 5:1 grid ratio. It doesn't clean up as much scatter, but it allows for a larger passage with which photons will make it to the image receptor without being annihilated. Right. So in terms of scatter cleanup, right, you got to look at things separately. So scatter cleanup is one thing. If you want the most scatter cleanup, you go with the highest grid ratio and the highest grid line frequency, which means more lines per inch or per whatever distance. But like I said, the other aspect is your margin of error or latitude. You have more problems with a higher grid ratio. And when we say problems, the other way to say that is grid cutoff, right? Any kind of problem is called grid cutoff. So to avoid grid cutoff, we use a lower grid ratio. Right? If you remember, no one ever uses these, right? A crosshatch grid where the lines go straight down and horizontally, so you have like little boxes like graph paper, that's almost impossible to use, right? That would mean your tube has to be perfectly perpendicular, right? And that's why we never use them, right? Because they're actually too good at what they do. So this is something we didn't have in class. This I saved this for the registry review. If you want to spend some time on this, you can. But so what do I mean? So in class and based on your textbook, so this is the reason I didn't do it. But this may actually be on the registry because the registry, doesn't have a sponsored textbook. You can't read one textbook and say, oh, I memorized that one textbook on image eval, right? Because there's other textbooks, you can't say that. I kind of have a feeling in my heart that because Bouchong is well established, maybe there's more questions from Bouchong, but I can't prove that, right? Where am I going with this? When the grid ratio increases, we need to use more mass. In class, we said just use 4 times. And we kind of just made it one number because it was easy to remember. But technically, it's different depending on the grid ratio. Notice, going from 5:1, it goes up to 3.5 and then goes up a little bit more to 4 and then it goes up a little bit more to 5. We made it easier, but you may get a question that says, how much do I change my technique if I'm using 70 kV and I go from an 8:1 to a 16:1? You need to use this formula, right? Which is known as the grid conversion factor formula. All right. So you got to know the table, which is this. so that you can plug in the information into this form. So it's pretty easy. It's going to be the first mass at the first grid ratio. So this might be, let's say in our example, we used 8:1. So the number 3 would go here. Mass number 2 would be X. Grid control factor number 2 would be whatever new grid you're going to. So we said 4, right? So it would be 3/4 is, I don't know, 5 mass over X. What is that? Once you plug in everything accurately, then you cross multiply and you get exactly what your new mass is. With all formula, as I've told you in class, you should always try to figure out what the answer is sort of going to be before you do the math. Like you should always have kind of, is the number going to go up or is the number going to go down, right, in your head. If you're switching to a higher grid ratio, right, and you don't do anything, then more photons will get killed. You have a possibility of noise. There are some general concepts you should know before you actually have to do any kind of math, if that makes sense, right? So you can, generally speaking, eliminate several choices before you even start a problem. Here's another little tip on multiple questions. So these are questions where it's like, I know you guys hate these, where it's like 1 and 2, 1 and 3, 1, 2 and 3, 2 and 4, you know. If, so I'm going to get to whoever raised their hand in a second. If you can eliminate, let's say, choice 3, then if it says 2 and 3, 1 and 3, they both have to be wrong. If you know that 3 is wrong, right? So that's a way you can eliminate some of the choices. If you know that, you know, of the sort of choice of choices, that one of them is incorrect, then wherever you see that, you can cross out that choice or set of choices. Okay, so let me see. Someone put something in chat. I think. According to the interwebs, no need to increase mass for air gap. Yeah, I didn't think so. Okay, thank you. We're doing okay, guys. We will take a small break at some point, but I feel like we're just getting started. So let's
Professor, there's a couple people that have had their hand up to ask questions. I don't know if you can see that.
Oh, some of them I see and some of them I don't. I'm looking at the chat and maybe it's not showing up in the chat.
Do you want me to just call their name out and they ask their questions? So,
well, so let's just take 2 questions. Someone asked me a question.
Yeah, Professor, I was going to ask a question regarding the
Okay.
grid ratio. So I just want to clarify stuff. So the lead line strip between the grids, it doesn't mean that if it gets narrower, the grid ratio is higher grid ratio, meaning lesser space, and then
that's correct.
Higher, more space means higher and lesser grid ratio. Correct?
That's correct. Yes.
Okay, I just want to get out there.
Yep. Anyone else?
Yeah, Professor. So you were saying that obviously if we have a high grid ratio, obviously it's going to clean up more scatter, right? Because it's closer together. But then you say, well, obviously to we're going to have to give more mass, and then obviously we're going to have more patient dose, and then all of these theories. But then you said also that even though we're going to have a higher grid factor, it cleans more scatter up, but then there's going to be more problems such as the grid cutoff, as you said. But for some reason, I don't really understand, like, how would that be more problem in terms of, because in a way it's doing something good, it's cleaning up scatter, then it's doing something bad, causing patient dose because we're upping the mass.
Okay, so here's what I'm saying. As grid ratio goes up, you can clean up more scatter. That's a good thing. However, because the lines get more narrow, closer to each other, right? One, we have to increase our exposure to make up for the extra loss in photons. But another very realistic thing to think about is grid cutoff. Your chances of something going wrong increase. So your margin of error is going to be higher. You have more chance of making an error when you have a higher grid ratio. So you get better scatter cleanup, but they are harder to use. And in particular, what makes something hard when you're angling, when you don't know your exact SID, like on portable mobile exams, right? Anything that's difficult requires a lower ratio. That way you improve your chances of bad things not happening.
So basically the beam that's coming is is going to like end up being cut off because of these spaces. When it's coming, it's just gonna like.
So think about it this way, right? If I'm walking in an alley between two buildings and I have a lot of space, right? That's very easy. If my grid ratio goes up, I'm reducing that space, right? So it's going to be more difficult for me to get through. If I'm a photon, I might just not get through at all.
Oh, too tight. Got it.
Yeah.
Okay. Got it. Thank you.
Mm-hmm. So what else? We have 6 weeks only. People looking at my oh, sorry. Grids don't differentiate useful or low energy photons. More lines means less access for the beam to travel. Well, it's not just more lines. It's also the distance between those lines. All right, let's keep going. So what is filtration? Filtration is for radiation protection, right? That's what it's there for. It's there to remove the longer wavelengths. Remember, those are the weaker ones compared to shorter wavelengths, which are more penetrating. So remember, we have a heterogeneous beam or polymorphic beam, which means we have various photons of different KV levels up until the KV that you set. So if you set 80 KV, you're really setting 80 KVP. The P stands for peak, but that doesn't mean it's all 80. It also means we're going to have 40s and 50s and 73s, right? And the idea is some of those photons that are so weak have such long wavelengths, the ones that even make it out of the patient, we can't do anything about those. But the ones that would likely not do anything, before they even get out of the tube, why not kill them? Because they're not going to be useful to increase our subject contrast. They like to use that term, right? So we can maintain our subject contrast and save radiation to the patient by using filtration in order to get some of the longer wavelength photons out of the mix before they ever even make it to the primary beam. Right? With filtration, remember, our intensity automatically goes down, right? You're knocking out some of the photons. Some of the photons are killed before they even make it out of the tube. So filtration affects intensity. Intensity goes down. But what also happens is average beam energy. That's the term that people like to use. Average beam energy goes up, right? You've seen me with this example before, right? You take test grades. If I take out like the 10 lowest quiz grades, then I have literally 10 less grades. But also the average, if I average whatever's left, the average grade will go up, right? So when it comes to filtration, intensity goes down, but the average beam energy goes up. Does everyone understand that? It should be a review.
Yes,
Okay.
Professor. It is on Bouchon. I think Bouchon has a better explanation to that. Two.
Whatever you use to get the answer right, that's good. Okay. So by the way, I would have used Bouchon. In fact, when I started the course, a while back, I was using Bouchon, but like, I don't know, 4 or 5 years ago, maybe more, I switched to the Radiography in a Digital Age book, the one that we've used, because I think that was better on the digital stuff, right? They were both pretty much equal to me for, the stuff we're talking about now, like filtration. Okay, what is the number you need to remember? Remember, 2.5 millimeters of aluminum equivalent, right? Added is about 1, right? And the rest is inherent. So if you take the inherent plus the mirror, right, you actually have more stuff in your tube that counts towards filtration than the actual added aluminum or copper that is used, right? So remember, the inherent is stuff that's there already. Parts of the X-ray tube, the glass, the mirror, right? Those are all things that will stop some of the weaker photons, right? But at the end of the day, we're at the amount of radiation that we use on average, 2.5 millimeters of aluminum is the number you have to remember. We talked about the general concepts here. Nothing really new, right? But when the average beam energy goes up, that's as if you have more kV, right? If you take the average kV of all the photons before filtration, it's going to be less than if we take the average kV of all the photons after filtration. So if that average kV goes up, kV up, contrast down. So does filtration affect contrast? Yes. Okay. Can you notice it? Is it hard to prove? Does it really matter because you could window the image, contrast with your mouse after the exposure? Yes, right? So, but remember, it's still the answer, even if you can't notice it visibly with your eyeballs. That's what I mean by the theory versus the practice of radiography. What's in the book might be true. Is it really hard to prove that there's slight anode heel effect? I mean, can you really recognize that one part, absorbed a little bit less radiation? No, that's why I do my lab with a digital dosimeter to actually look at a number. So how much does it really affect things in real life? Not much, right? But you have to put those things aside, right? When you're taking the test. So collimators, they're still being used, I hope. What do? They reduce some of that scatter. The scatter's diverging. So if you pull in your collimator leads, right? In other words, collimate more, you're going to get rid of some of that scatter. So your contrast will go up. So collimation increases contrast. And because you're cutting off some of that scatter that doesn't reach the patient now, then you've saved dose to the patient. So collimation is like a win-win. Dose will go down and contrast will increase. So we should collimate as much as we can without cutting anything off, obviously. And I don't see it, to be honest with you guys, in clinic, but that's a whole nother topic. Right. We should be collimating. And cropping is obviously not the same. When you fix an image after the fact, that's not going to do anything for radiation protection, right? You've already exposed the patient. So not really acceptable, even though I know everyone's doing kind of stuff. Okay, motion. So motion, remember, is either the patient is actively, consciously thinking about moving, so they just move. That would be voluntary. If it's unconscious or something that is automatic, like breathing in and your heart beating and peristaltic waves going down your esophagus, those are all involuntary. You can't tell someone, I mean, I suppose you could say stop swallowing, but you can't say, stop your heart, please. So all we can do is reduce the time and increase the MA, right? That's the reciprocity law again, right? All digital imaging, at least at this time, not really good at fixing the motion blur that you get, right, after the exposure. Maybe we'll get there one day, you know. There's a lot of things that happen now that I never thought of, 30 years ago. Sometimes motion is known as false images. It's like several images on top of each other that are off by like less than a millimeter each, that when you look at them in total has this blur look to it. So if you see that term false images, it's related to motion. Okay. Is there anything new here? Well, I don't know why this doesn't really seem to match. Let's just keep going. So anode heel effect, again, you're not going to see this too much in real life. Just remember that based on the way the anode is designed, the heel kind of sticks out a little bit, right? See how it kind of sticks out to the left towards the anode, which means it's not sticking out towards the cathode. So more photons are able to make it through the cathode side. That's why the intensity is higher going to the right, going towards the cathode. Because the anode sticks out here, you have photons that were about to make it out of the tube, but then got reabsorbed. So because they got reabsorbed, the intensity towards the anode side goes down. So you have higher intensity towards the cathode, lower intensity towards the anode. The idea once upon a time was, well, if you have a thick part of the bone, like the femur at the femoral head versus towards the knee, you should put the femoral head part of the femur towards the cathode side of the tube to take advantage of that increase in intensity. Again, this is one of those things that is pretty much going away because you can fix the image. And when you try to reproduce this in a lab, it's kind of hard to do. But it is a pretty big difference, right? 25%. This, you're not going to see much anode heel effect on like a finger, right? Because if you have a small object, what would be the difference? 90 versus 105 percentage-wise, right? The difference is if you put something really thick here versus something that same thickness on the complete other side. So when I do this experiment, either I use the digital dosimeter to just show you the numbers changing, or once upon a time with actual X-ray film, you could see a little bit of a difference, right? If you put the thicker side towards the anode and didn't take advantage of the intensity, in fact, the intensity is lower at that point, it might have looked a little grainy or a little bit too light. But again, this is something that's not really happening.
Professor,
but for the record, you still need to know the rule. Yes.
I have a question. So would you say that the closer it is to the anoid side, the more dosage?
No. The closer, it's the
I mean,
opposite.
not more dosage, less dosage. My bad, because less intensity.
Then yes.
Okay.
Yeah. But you have to know two things for anode. They're only going to ask you two different types of questions. One is just, is it more or less? And the other question is, if I have a thick object, where do I put it to take advantage of more intensity? You would be towards the cathode side. Right?
Okay, noted.
So, yeah. Let us keep going. Size and pathology, not much you can do there, right? In terms of what the actual patient is. And by the way, you will get one of those questions on like hyperstenic versus stenic versus astenic. So make sure you go over those. Because there will be like one question. So patient factors, there's not much we can do, but they affect a lot of things, right? Larger patients are harder to image because they naturally create more scatter, right? They just kind of do, right? Because most of the scatter is coming from inside the patient. If you have more tissue because you're larger, then you have more atoms, more electrons, more potential for scatter. Yes, don't worry. about your laptop. As long as you're able to view the presentation, that's nice. Okay, but thank you for the message. I'm multitasking, guys. I'm trying. You know, they say multitasking doesn't actually work. But I'm doing my best anyway. Okay, so I know this is a long list about what pathologies, I'll get to the chat in a second, what pathologies are considered destructive, meaning you would lower your exposure, or I think it's constructive, meaning you would increase your exposure. So, you know, the one I always use in class is osteoporosis. It gets rid of some of the calcium. So literally the bone is less dense. Its average atomic number has gone down. So that means you should use less radiation. That's not going to be an issue because of, you know, radiation creep and digital things. So you can probably, you know, not change anything in reality. It's when you have a constructive disease that like Paget's disease, which would be the opposite, is an increase in calcium and a hardening of the bones. Then you need more radiation. And if you didn't increase, you run the risk of quantum model not having enough photons, which results in noise, right? Although once upon a time, you had to worry about literally increasing or decreasing. Now it's more like increasing where you need to and staying the same if even in the past you had to decrease. So do you memorize every constructive versus destructive disease? I mean, there's only a few thousand of them if you take, you know, the medical dictionary. I don't know. I would not waste too much time on this, right? If any. You know, if you did okay in school, and if you're getting whatever questions that might be related to this correct, even if you're just guessing well, right, then go with that. Don't try to memorize, like, I don't know, the 50 top diseases in the United States, you know, just to pick something. I wouldn't bother doing that.
They always seem to have emphysema, pneumonia, osteoporosis. Those are always on everything.
Those are the big ones. So know those. Yeah, don't go much beyond.
Ascites also comes out sometimes.
Ascites comes up a lot, you know.
Tuberculosis too.
Yeah, so go, I mean, if you want to go with, you know, the top 10 or top 20, but don't look at every obscure thing. Don't waste any time on it. Okay, two-part receptor angle, all that kind of good stuff. So we kind of take them briefly one at a time. So whenever you angle the central ray, no matter which way you angle it, you will elongate the anatomy in that direction. So I angle caudally towards the feet, I angle anatomy caudal. If I angle cephalic towards the head, same thing. If I angle, which is rare, you know, medially or laterally, you know, actually kind of pointing the tube towards you when the patient's supine on the table, which, you know, you never hardly see that. That's going to create elongation.
An example of this would be the foot, right? The foot is already foreshortened, so you would have to angle to compensate for that, or?
That's right. But it's also used to just throw structures out of the way of other structures. So we do an axial angle on the clavicle to try to bring the clavicle above the ribs, just to see it better, literally, right? So sometimes it's based on the anatomy, sometimes it's based on getting rid of superimposition, to reduce, as it says down here, to reduce superimposition.
And this is shape distortion, right?
This is shape distortion. It comes under shape distortion. Yeah. Size distortion is the object gets bigger or smaller, but its literal shape does not change. The proportions of shape do not change. Magnification is easier to deal with, right? If the question is, would you rather have shape distortion or size distortion? The answer is always size distortion. It's easier to get your brain to understand something that is still round, just bigger, right? A penny versus a quarter It's just the quarter is bigger. But you change the shape and you turn it into something that looks like a football, or kind of weird on one side, but not the same on the other side. That's harder to make sense of, right? So if you have to choose distortion, which one, shape or size, you got to go with, I'd rather have size distortion than shape distortion. So how can you get distortion? It's particularly elongation is only the tube. Foreshortening is the other half of that. Foreshortening is if the, I can't see myself, let me try to get me on the screen. Foreshortening is if the part itself is angled. That's going to foreshorten the way it looks on the image. Or if you also angle the image receptor, right, like the Bucky, that can create foreshortening. This is one of my favorite labs, as you know. We can correct for this, right? But a certain amount of angling of the tube can elongate something that's been foreshortened to get you back to like normal.
Wait, so you can never angle to foreshorten?
You can angle the tube, excuse me, no, not the tube. You can angle the part and you can angle the image receptor.
But not the tube. The tube doesn't have to do with any foreshortening. Not even if
Correct.
you do it caudally. No?
Tube is just elongation.
Okay. I didn't know that. That was
Yeah.
Professor, I want to ask a quick one. I usually get confused with this. So, for when you angle the tube, is that size distortion or shape distortion as to when you just flip the image in response to the IR?
So without anything changing, if all you do is angle the tube, that is elongation, and that comes under shape distortion, right? Shape distortion, it's either elongation or foreshortening, right? If you change only one thing, it can't be both. Now, if you angle the tube and create elongation, and then angle the image receptor to foreshorten that elongation, you can fix things, right? And what you see in this image here is you can also have magnification and foreshortening, you know, at the same time, right? So if you have the image receptor at an angle, this part of the image receptor now has less OID than this one. So this size is magnified. You can see they even drew the picture to make it look big over here. So you can have a combination of magnification and shape distortion at the same time. So that's possible. And that, in a way, that happens all the time, because objects within the body are not automatically parallel to the image receptor. Just because you put something supine doesn't mean anything that's inside someone's abdominal cavity is going to be exactly, you know, parallel to the tabletop, right? Things are in different places. So this is going on in the body in every radiograph you do, for the most part. So the formulas, they're here, but I'm not going to spend time, you know, really going over them. Just make sure that you do, and that you take a lot of questions related to this. If you want to take things to, you know, another level, which I think I may have mentioned before, when you're reviewing, make sure that you also review every question you get correct, to make sure you know why you got it correct and that you didn't just get lucky, right? So you're going to review the ones that you got right. You're going to review the questions that you got wrong, of course. Then you're going to decide how much effort it goes into that particular subject to decide how much you want to study it. And guys, don't forget some of the patient care stuff, especially the legal things. there's only going to be maybe one or two questions on, I don't know, torts or respondent superior or those other terms. Assault and battery. Make sure you know the basics, because you don't want to get that question wrong if it's going to be pretty easy. It's just, memorization. You just got to know the terms. There will be some situational questions related to patient care. I'm not quite sure how exactly to study. Hopefully your clinical experience has helped you to help you answer those kind of questions. Also for strictly anatomy questions, and I may have mentioned this in class, from what I understand, some of the questions now are just click on the mesenteric artery. It's not going to be an image that you might see on our tests. Our tests are old and we're not that, technologically sophisticated. So we will put lines with A and another line that points to something else that is B and another line that's C. They don't have to do that on the registry. They can just say, click on this. That makes it tougher, right? Because you don't have any process of elimination. You literally just have to click on the anatomy. I don't know if they give you how many millimeters they give you to be correct or not. But getting back to this, radiographic sharpness is another formula you might see, right? Now we're moving into a different kind of level of stuff here, which is why this is up here. So technique charts, there's really only a big difference between fixed technique and variable. So we'll go over those in just a second. If you see the term APR, it's an automatically programmed technique. Those are everyone's using those now, right? Those are the techniques that pop up when you choose knee exam, right? Comes up with a certain KV, comes up with a certain mass. And that's generally designed to fit in so that your exposure indicator and your DI, deviation index, are within range. I don't know. Whenever I go to clinic, I see people under and overexposing just constantly, but no one is getting rid of those images, unless it's really, really bad. But that's another story, I guess. So APR is like the built-in menus of techniques, right? No one's ever using a caliper to kind of decide how much KV. But if they ask you, right, again, the registry will ask you things that you never do, right? You take the thickness of the part, right? So let's say it's 10 centimeters. You multiply it by 2, so that would be 20. Add another 23, so that's 43 kV minimum, right? So it goes by centimeters. And then you go higher depending on the generator. So we talked about generators, and Professor DeVito talked about generators. You have single phase, triple phase, and then high frequency. Everyone's using high frequency, but the registry may mention a lower ranked generator, like a single phase. So what are the differences? Because they'll want you to know that. The differences are in the amount of KV that you set. What is the proportion of the photons being at that KV that you have created? So when you use a single phase generator, on average, all the books will say the same thing. You set 90 kV. Most of the majority of your photons are going to be about 30, right? About 1/3 of what you set. So if you set 90, 30 is 1/3. As you get a more efficient generator, so triple phase, high frequency, at the high frequency, the best generators that we have, they're the most efficient. You set 90 kV, approximately 95% of your photons are going to be at that 90 kV, right? What does this mean? That means a high frequency generator will lower radiation to the patient, because you don't need to use as much, because it's going to be more efficient. So a higher, more efficient generator, high frequency versus single phase, means you can lower your exposure.
Would it also decrease contrast?
So yes, well, let me think about that for a second. If you have a more efficient generator, it's like increasing your KV. So in that manner, KV up, contrast down. So your contrast might go down. I don't think it's noticeable in reality.
But it is a factor, right? So like say if they say compared to let's say a high frequency generator compared to let's say a lower frequency generator, what are some of the variables that a high frequency has compared to a lower
Yeah,
frequency?
I guess you would say a high frequency would reduce contrast a bit.
Okay. And then also lower dose.
Well, it gives you the ability to use lower dose because you're going to have more photons that are stronger. It's just your mix of, we said that the beam is heterogeneous, right? That you have different KV level photons in there, but the higher frequency generator, the more efficient one, is going to have more photons at or close to the KVP that you actually set.
Would it also be faster, or is that not even a factor?
I don't think that's a factor. That's governed by your time.
All right.
So I don't think it would make your, if you so here's the thing that you shouldn't overthink. I'm going to overthink for a second. This is what I don't want you to do. If you overthink it, when you go to a high frequency room, you could technically use less exposure, which means you can potentially have less mass and or less time, or I should say less MA and or less time, which would then decrease the time. So if you had a question that said, well, this patient has a chance of moving, should I use the lower frequency room or the higher frequency room? You go with the higher frequency room because it could lower the time potentially more in a high frequency room and still get the exposure that you need. Again, that's overthinking.
Professor, so I didn't understand this at first, but your last explanation gave, because that's the angle I was taking to it, because you said if the generator is high frequency, there's chances. So I was thinking about, because in my head I was thinking there was going to be more force pushing the mass toward the patient, then that could lead to more dose. But however, the time has to be reduced to compensate for the excessive MA that is driven toward the patient. So that was why I was confused.
Yeah, another way to look at this is if you have a beam, right? Let's say 50% of that beam is much lower than what you've set on the console, right? 50% of it is much lower. Then you go to a high frequency room, and all of a sudden you're at 98% of the photons are going to be at the level that you set. So they're generating much higher, way more than 50%. You can then lower your exposure dose, either MA or time, by close to 50%. Right? So you can kind of look at it mathematically a little bit.
One more question.
Mm-hmm.
On high frequency. So high frequency also has high DQE, correct?
Let me think about that. So detector quantum efficiency is more about the detectors. A higher frequency room.
That's more like signal noise ratio.
No, because usually, but doesn't high DQE result in less exposure? And then if you're also saying a high frequency, which results in less exposure, wouldn't it also correlate?
I guess indirectly, it's you're almost saying the same thing that a wrist gets to use less radiation than a shoulder, thus the DQE is better. That's kind of what you're saying. It's if the DQE is increased, it's indirect. It's indirect because you can just lower the radiation amount from the onset. So I don't think it has a direct effect on DQE.
Oh, okay.
Catherine, write that one down. But I don't think so. All right, so when it comes to charts, right, if it is fixed, then the KV doesn't change, right? And only the mass changes. So if the part gets bigger, you use more mass, but your KV remains the same. Variable KV is just that. It means you change the KV. Right? Which one is better, I don't think is really discussed, right? I don't know. Maybe you get one question on this. Has anyone gotten any questions on fixed versus variable technique charts for any of the questions you've been doing?
There was one on our review the other day.
Really?
It said, like, which is the technique chart that should be used if your anatomic part size increases. Variable KVP fixed mass, variable mass fixed KVP, AEC or APR.
Well, that's a lot of choices.
It was
well,
variable KVP.
Variable KV. Yeah, variable KV. So here's the thing, and the reason this is why I said variable KV, because I know if you don't use enough KV, you get noise. Period. If that's something you're worried about, and you have a fixed KV that says 76 KV, and you can't go beyond that, right? And you get something that needs 86 KV, then it doesn't matter how much mass you have. So you need to be able to use higher KV, thus variable KV. That was my thought, right? So one of the things you should ask yourself when you get questions correct, especially if you kind of guessed and wasn't sure, when you see the answer, make sure that your logic in your head makes sense for why the answer was correct. Because if you just kind of got lucky, then you might not get lucky again when it comes to a real question on the registry.
Well,
so you got to
Professor, I
double
have
check.
a question.
Yeah, Duran, how you doing?
Yeah, but also with the variable KVP, like say if you have a patient, you're doing like a pelvis and you have a bigger patient, then you'll want to do a variable KVP because you want to make sure you get enough penetration for that bigger patient part thickness.
That's right.
Right?
Mm-hmm.
Or you can use a grid.
Yeah, grid changes things too. Okay, so let's go over this and make sure we hit everything. So the chart has to have the position or projection. So when they say fixed KV, there's different KVs for different parts, but sometimes a big pathology can change that drastically. That's where the variable KV might be better. So it's not to say that fixed KV is always bad, right? Right, they all have to give you your MA, your time, your KV, and your SID, and give you a certain part thickness. This is an old term that's going away really quickly, is speed. So here's an example. I should have just went to this next slide. I don't have all these memorized. So notice this is particularly for a knee. This is a variable KV because obviously it's changing, right? Depending on the part thickness. Okay, let's keep going. So this is just added information. I don't know how much of this stuff you need to memorize, other than ionic contrast, like an injectable. Generally speaking, we don't want to use too much KV because it could burn out the contrast. The opposite of that is barium. Barium requires a definite increase in KV. So I don't know why I have too much. I have more stuff on fixed variable that I want. Yeah, I mean, who's using plaster anymore? But remember, there are a few rules about you have to increase if you have plaster. You have to increase even more if it's still drying and it's wet. Splints, fiberglass splints, no change in technique. Those are the main things to remember. Oh, here's the list of different things. Again, I don't think you need to go over all of these, right? Although a lot of these seem like are the ones that you mentioned earlier. Pediatric considerations. So kV, you have to go up in kV for barium, below 75 if you're using intravenous types of contrast, ionic or non-ionic. So patients, we know that they as they get older, you use less exposure. As they become more muscular, more exposure, right? A lot of these things are kind of, you can figure this out. Just common sense things. Automatic exposure control is a game changer. Overall automatic exposure control, what's important to make sure you have the correct cell and that your positioning and alignment is excellent, right? That's the key to making AEC work for you. If your alignment is off and you're partially on the cell but not fully on the cell, that's going to make the exposure turn off faster because you're going to get more raw radiation hitting a part of the cell. That could lead to a quantum model, right? Because the exposure time gets cut and then you get a grainy image with noise. If you have the wrong cell, that could lead to an overexposure because the cell that is activated might not be feeling any radiation. Let's say the one that's activated is off to the side. It's waiting for the radiation, and the radiation is hitting the patient, but not the cell. Then it stays on longer, and you overexpose the patient. There's a few different scenarios, right? Any questions on these, Catherine? Do you remember?
Yeah, we had one that was in a lateral lumbar. If the spinous processes are centered, what will the result be if using AEC? Underexposure, overexposure, either under or neither under or?
That's an underexposure.
Mm-hmm. So if you're underexposing and the part that's, I mean, if you're off centering and the part is thinner than the part that you have it set up for, it's always underexposure. But if it's thicker, then it could be, oh, well, vice
That's
versa.
right. So in this example, no, but in this example, you're right. The reason why I guessed underexposure is because the spinous process is a little bitty thing. It's
Mhm.
like sticking out your finger and pointing compared to the rest of your hand, right? So if you're centered over the finger that's pointing, it's going to be an underexposure, not to the spinous process itself, but to the body of the vertebra is going to get underexposed because it's going to turn off faster because you're centered on the thin part.
I have a
So
question.
that's the catch. So Zabir, just before you go, so there's a catch to every question. The catch to that question is knowing that you need to be centered over basically the thickest part of the anatomy for AEC to work out well.
Yeah, I was
Go
just
ahead,
gonna
Zabir.
say that because I quickly read the question and just saw that it was centered on a part of the spine. So I was like, oh, then it should be fine. But I wasn't paying attention to that it was spinous process versus body.
Here's a quick question for anyone. How many times did you get a question where the answer was actually up or down? I think that's rare. It's usually there's usually an answer. But always read the explanations too. If you have questions where all you have is the answer choice, those aren't as helpful when you're studying. You want an explanation. Zabir, did you have anything?
Yeah, my question was if say a body part was over the cell that is supposed to be used, what would that be a result of?
Well, that sounds good to me.
That's good, right? And then if it's under, that's when it's underexposed?
Well, hold on. So you said if the part of interest is centered on the cell and the cell is activated,
No,
that's
above the cell. I'm saying above the cell.
Oh, okay. So here's
Like
the thing.
below the cell, like you put an exam in and it usually shows you the cell, but you centered below or above. Like what would that indicate?
Okay. So that would generally be an underexposure and possibly noise. So let me give you an example.
So would that be like a both scenario where it could be under or exposed if it's above a cell or under a cell?
No, I don't think it would. So let's take an example. Let's say, I guess it might depend on the part. Let's take a knee. If the knee is perfectly centered on the cell, no problem. If you are above the knee and the cell is on the portion of the femur that is going to be less dense in general, that might be an underexposure. If it's in the tip fib or lower, then it's definitely an underexposure. But here's another example that could be different. If you're in the hip and your objective is to get the head of the femur, if the head of the femur is on the cell, that's good. If you are below the head of the femur, that could be an underexposure because it's not as thick and the radiation turns off. If it is above that, then you might be into a fairly thick portion of the pelvis. So it's tough. You have to decide wherever
I'm only asking this
the
because
Yeah.
there was a question on the RAD review, I believe,
Mhm.
that we took recently. And there was a question where it said it could be either underexposed or overexposed, and that was the correct answer.
Yeah, so that's I think that might be right. Because it depends on what the anatomy is. If the anatomy is thicker than the part that you would have it on, then it's going to stay on longer to penetrate whatever's in front of it.
Yeah.
If it's anatomy that is thinner than the part that you want, then it shuts off too soon. So it can be either or.
Yeah.
That's
Yeah,
why I
it
was
fills
trying to
up
give
the
you
cell too quick.
Yeah,
that's
Yeah,
why I
the
was trying to give you two different examples. So that would be a good answer where it could be both,
yeah,
unless they give you specifics.
the
Yeah,
question was the area of interest has to be placed directly over the selected detector to avoid which of the following: overexposure, underexposure, decreasing contrast, or increasing contrast. And you
and
have to pick two out of the four that apply.
that was the question I remember. I got it wrong, but that's why
That one's that's a little tough. Send
well,
it to me for one, but two,
I
the
think it's the
choice.
anatomy of the question. So that's like the kicker. Like if you pay attention to the anatomy, that means the thinner it is, the more radiation is going to hit the AEC. It's going to cut it off quicker. But if it's the thicker part, then it needs more time to penetrate, so it stays on longer. So I think the question is really in the anatomy part.
Yeah, I think you have to think about what the anatomy is. What was the answer you said?
I think it's
It's
both.
overexposure and underexposure. So it's basically you want to make sure that your part is aligned to avoid overexposing or underexposing. It
Okay,
has nothing to
not
do with contrast.
not contrast. Okay,
Correct.
good. I'm okay with that. Okay. Yeah, AEC is tough. You're going to get like two or three questions maybe related to probably a situation that might increase the exposure, a situation that decreases the exposure, and then a question related to, does it add or reduce dose to the patient, and how does it? I don't think it's going to be contrast related that I can think of.
So, Professor, can I just give a scenario? So, because I'm kind of trying to cash it up. So, if for example, I'm trying to do an X-ray of my forearm, and then I'm standing,
Your forearm, did you say?
yeah, forearm, yeah, and I'm standing by the cassette, and then mistakenly, the cells are centered between my elbow and the forearm. Would that result in what they're saying? Because the cells is detecting a much more thicker part of the anatomy, which is my elbow and versus the forearm. So it's kind of not giving the accurate exam or result.
Yeah, so there are a million different scenarios, but all I can say is what you should look out for is one, in a perfect world, you're perfectly centered. Two, a forearm is probably not a good example because that should not be done AEC at all. Usually AEC is for larger parts that are somewhat hard to position. Spine, hip, things where you can be off. In fact, the hip is one of those things where you add the +1 or +2 to give yourself just a little bit extra exposure, just in case you're not perfectly centered on the head of the femur. So you really have to see, you got to make sure that the correct cell is on. And the most important thing is the alignment, not even so much the positioning, right?
I got one more question. I'm sorry. If say there was let's say they give you a scenario-based question about something in the lungs and there's pathology, right? Would I ever say where would you center the pathology via cells?
No, I think that's reading into it. I think it's too much for them to give you that kind of information. I don't think it would change the AEC. That's a good reason for using AEC, because whatever it is, if you're centered correctly, it'll adequately penetrate.
So you would
that's a rationale for using AEC.
Oh, okay, so you would use AEC for if you had pathology, right? Okay.
I mean, don't we use AEC on just about every chest X-ray we do?
Yeah, this is true. This is true.
So, Professor, I have a question. So, at HSS, when we do like an AP lumbar, we use AEC, but for the lateral, we take off the AEC and then we just do adjust our technique manually because of the thicker part. So, is that the correct way you say to do it, depending on the thickness of the part?
That's their rule. What they're saying is your margin of error is higher on the lateral than the AP. It's harder to position. You have that same, relates to the question Catherine was talking about the spinous process. If you take it off of AEC and just use a better technique, chances are you'll get a satisfactory image. But I think that's just their rule. It's not a bad rule. But I think if you are accurately positioned on the cell for a lateral, you should be able to do it AEC. It should work. I'm just reading the text here. We do AEC for lateral because it's harder. Oh, we don't do. Yes, but it's harder is not an excuse for slacking off on positioning and alignment. If you're good, you're good. So I guess it depends. You could also say, why not just use AEC and add +1 or +2 it, just in case you're too posterior. That would work also. But instead of doing that, they just don't. The policy at HSS is to just use your own technique. All right, guys, I feel like I have to speed up a little bit. So let's keep things rolling just a bit here. Okay. Okay, we talked about automatic exposure control. And guys, if you have any weird questions that you don't understand, send them to me. And I used to do that at clinic all the time, right? People would be studying at clinic when there was no case to do. And occasionally I would see questions where I don't agree with the answer, like SEA in particular. The only other thing about AEC that I want to mention is, if you have the AEC set for the table, but you have the two pointed at the patient, horizontal beam, and they're standing, that's an overexposure to that's an overexposure to the patient, because the radiation never hits the cells that are in the table, and it'll just stay on, right? Unless the room is smart enough to realize that you're not facing the table. So that's the other kind of question they can ask. Is just literally getting table versus upright wrong. Don't forget there's a minimum response time. Review the lecture and then look at your AEC questions and see how you're doing, essentially. AEC is one of the best things, but it requires your alignment and cells to be correct. So the +2, increases, about 25% exposure. And that's designed because sometimes it's hard to get exactly on the cell, right? If you're half on and half off, that's going to change your exposure. Okay, digital imaging characteristics. So we've gone 2 hours. Can you believe we've gone 2 hours already? So I say we take a 15-minute break and then we keep going. So let me stop sharing for a second.
Could I ask a quick question for AEC?
Mhm.
So is
Yeah.
it true when you do manual technique for the lateral, it's going to be a higher technique than for the AP because you want to penetrate more?
Oh yeah.
Okay.
Yeah, lateral lumbar
Mhm.
is going to be higher than because you got all the pelvic stuff, especially for like L5S1.
Okay, thank you.
Yeah. Yeah, most laterals are, hand lateral is more than a PA hand. Most, not every lateral, but most of the laterals off the top of my head are higher exposure. Not sure about the skull in every case. Skull might be a little different. Okay, so let's reconvene at 3:15.
This meeting is
We have about an hour. There is no possible way, unless I speak very, very fast and skip all sorts of things. So what I'm going to do is go about the same speed, but I'm going to probably add another hour, hour and a half. Not today. I'm going to just record and send out a second video, right?
It doesn't
'Cause
feel
I
the
actually,
same.
Hmm?
I said like it doesn't feel the same.
Oh, it doesn't feel the same unless it's live?
Yeah,
Well, you guys can still email me and ask me questions.
true. Thank you.
Okay, so without further ado, let me go ahead and share, because now we're getting into the digital stuff. And I don't want to go too fast on this. So we're going to talk about spatial resolution, and we'll get into indirect versus direct. We'll get into detector elements, and we'll talk a little bit about pixels and matrix size. So
Ashley's
yes.
Ashley's asking for you to let her back in.
Oh, okay. Yeah, let me, I'm going to stop sharing as the easiest way and fastest way for me to do that. But usually she should just try because it usually shows me when someone comes in, like a little thing comes across, like admit or don't admit. And I don't see that. Just tell her to try again.
I just got it. She said, please tell Lobel to add me back in.
I could add her if I saw her, but
Hold
it's
on,
not.
I'll tell her.
Yeah, let her know. Just try again. And if it pops up, of course. All right. So where are we here? Okay. So we're starting off with spatial resolution. What are the things that affect spatial resolution? Well, we know it's things that have always affected the sharpness of the image, like OID and SID. But on the digital side, we have things like the pixel and the matrix. So when it comes to pixel, smaller pixels mean you can illustrate smaller objects, which means your spatial resolution increases when the pixel size is smaller. Pixels are small to begin with. They're usually sub-millimeter, in other words, less than a millimeter. If you ever do the field of view divided by matrix size, which is the formula for pixel size, and that's in the presentation, so you'll see it. If you ever get something that's more than 2 or 3 millimeters, you know you did something wrong. That's another one of those kind of, you should know what answer you should expect before you even do the math, right? So just about any question you get, you should kind of have an idea whether the number goes up or down or what the range should be. So anyway, oh, here she is. The other thing that relates to spatial resolution is the matrix size. So the pixel elements are laid out on your matrix, which is rows and columns that make little squares. And those squares are your pixels. And we have matrix sizes that are very high in radiography compared to other modalities. So you can have, a rather small matrix, 256 by 256, all the way up to like things like 4096. So 1024 by 1024, 2048 by 2048. The higher the matrix, provided that the field of view stays the same, that's the border around your matrix, the smaller your pixels will be. And we already said smaller pixels mean better spatial resolution. Again, spatial resolution, I shouldn't say again, but it's a review, is the ability to distinguish small objects from each other. It's not to know that they're necessarily different. That's the distinction between contrast resolution and spatial resolution. So spatial resolution is just being able to see objects, right? If the shade of gray changes and you're able to see those differences, that's contrast. So spatial resolution is more about countability and sharpness than it is being able to distinguish attenuation differences as manifested as different grayscales. That's contrast, right? So spatial resolution, again, is like sharpness. We can look at it in terms of line pairs per millimeter. The higher your line pairs per millimeter, the better your spatial resolution. Essentially, you see this 1.6 over here, to see the spaces between the lines. If you have two objects in between those two lines, they'll blur together and it'll look like maybe one object. That's less likely to happen the thinner the space is between these lectures. Just tell me how much you take. So the idea is if you have a smaller thickness between the lines, you can take those two objects that blurred together up here, and in a theoretical way, down here, those two objects, one of those objects falls into one line pair and the other object falls into the other line pair, and then you can count them as two separate objects, in theory. So how do we figure out spatial resolution if we are given the size of the pixels? Well, we can use this del pitch formula, or spatial resolution formula, where the spatial resolution is equal to 1 over 2 times the del pitch. So the del pitch is either the center of one pixel to the center of the other, or just really the size of the pixel. Notice they're both 0.1. You could use either A or B, right? And then it's 1 divided by 2 times whatever this is. So for this example here, the del pitch of 0.1 millimeter results. So 0.1, so it would be 0.1 times 2. You could do this one on my calculator real quick. Generally speaking, we're not going to do the calculations, but we'll do this one. So 0.1 times 2 is equal to 0.2. 0.2, 1 divided by 0.2, 1 divided by 0.2 gives you 5. So 5 line pairs per millimeter. There's a lot of formulas, and I can't even guarantee if I went over absolutely every possible formula. So you might see something in a question that you get from one of the review things that you're doing that you've never seen before. Double check and see if it's vaguely in any of the content specs. Remember, the content specs doesn't tell you everything. They give you different categories. And also you should know, the whole test is not my stuff, right? There's more imaging procedure stuff than there is image eval, which is my class. And some people do very well on my stuff and for some reason not so well on patient care. So everyone's a little bit different, right? And the object is to, at a minimum, get a 75, right? Hopefully we do a lot better. But you shouldn't be unhappy if you get a 90 and you feel like you should have got a 95. Remember, the object is the pass. So a detector element, right? These are small. These are what are taking our photons up and hopefully creating what we call a measurable event, right? So, a photon comes into a detector. If it's an indirect detector that you have in a CR plate, remember, indirect means X-ray converted to light, and then that light is converted to ones and zeros, like a digital aspect that the computer can work on, like an array processor.
So professor, when it becomes the numbers, that's basically I forget the word that they call it, quantization or something like that? Or am I overthinking?
I'm not sure if that's the term. Someone could, while we're going, someone could look that up.
Okay, I think I saw like a question from Rad Review that was similar to that, but maybe I'm overthinking.
No, it might be. That might be. I mean, there's a lot of different ways to call different things, but indirect means X-ray, which is analog data, to light, which is also analog. But then we need to turn digital. So it's analog, digital, and we need a analog to digital converter, or ADC, to make that last indirect step where we go from electrical signal to ones and zeros. In a direct detector element, we go from X-ray, think about the word, we go from X-ray directly to digital ones and zeros. That's all pre-processing. That nothing is going on. It hasn't hit the histogram or any of those other things. So having smaller detector elements mean we can gather up more information, but also each of those elements, if you remember, there's a cross section, is probably in here somewhere. There's a term known as fill factor. Fill factor is the surface area that's actually responsible for interacting with the detector. So you want a larger fill factor, because anything outside of the fill factor are like electronics. And if a photon hits any of those little electronics, then it doesn't get counted, right? It doesn't turn to light, or it doesn't turn to an electrical signal, like nothing happens, right? So the bigger you can make your surface area, the bigger you can make your fill factor, the better. Of course, that means miniaturizing every other little electronic thing that's part, and this is what makes, flat panel detectors $80,000, right? There's a lot of technology that needs to go into making very small things. Okay, let me just check the chat real quick. Quantization happens during the ADC, where the numbers turn into a gray value. Okay. I don't know. I kind of disagree with that. Because the analog to digital converter will convert electrical voltages into ones and zeros. I think it's not until you get out of the ADC and into the array processor where those numbers are then converted to actual grayscales. So I'm not sure I'm going with that. But I mean, it says what it says. I'm not discounting, where you got that from. I just don't agree with it. Okay. So getting back to where we were, a lot of the flat panel detectors are 17 by 17. No, I don't know how that's neither here or there. We need to make them big. And the good news for me is I already stopped talking about CR. So the juniors didn't even get this stuff, because they, even though they're done with my class, are going to be taking the registry after March next year. So I had to pre-plan. So here's the formula that I did on my calculator a minute ago. Pixel size is field of view divided by your matrix size. So when you have 512 by 512, you divide that into your field of view. Just remember, if the field of view is given to you in centimeters, let's say the field of view is 30 centimeters, you have to convert that to millimeters. So that 30 would be changed to 300. That's another one of those where I don't change it. I get an answer. I make that one of my choices, and it's the wrong choice. That's what I meant by, how to get the incorrect answer. And if you're really savvy and you get the answer right, but then you realize Oh, the reason, so that's the catch in some of those questions is just mathematical, and they just figure it out without you converting something first. Okay. So del size, generally speaking, the difference between long wavelength and small wavelength. And where are these wavelengths coming from? They're coming from the object information. So if you're in what we used to call the frequency domain, where all objects are represented by various frequencies, we can say that shorter wavelength, also high frequency, goes with smaller objects and more detail. Bigger objects are lower frequency and longer wavelengths. Remember, L goes with L. That's one way to process objects. It's also one way to increase the spatial resolution, like edge enhancement, or to use a digital filter and do noise reduction and try to improve contrast a little bit. By taking some of the frequencies out, so let's say you take some of the longer frequencies out, the lower wavelengths, that will, longer frequencies, excuse me, higher frequency and shorter wave. If you take those out, you're getting rid of some of the smaller details, but you're getting rid of some of the noise as well, and that will improve contrast. So that's the way some of the digital filters work. So you may have heard me talk about high pass, which is increasing spatial resolution, high pass filter versus a low pass filter. They all work with frequency and wavelength information from the structures in the body. And when we do this type of reconstruction, you are using the Fourier transform, or FT for short, right? It's what we talk about in MRI, but the Fourier transform is also breaking up information into frequencies. So here's that del, right? Here's the surface area. If we can increase that surface area, which in this case apparently is about 80%, if we made it 90%, what would be the ramification? The ramification is you'd be able to use less exposure. Okay. So if you're able to count more photons, you don't need as many photons. So if this were able to increase the surface area by 10%, you could approximately cut the dose by 10%, right? So that's really why we're even talking about this, right? Because it's important. If we can make things like the TFT and the capacitor smaller and give us more surface area to capture photons, because if they hit here and they hit here, they're not counted, right? That saying, if we didn't reduce the dose, right, and all we did was keep the dose the same, but the fill factor increased, then we'd have a higher signal to noise. We'd have more signal compared to noise, right? And that's the goal. I mean, I've never heard of anything where we want to lower the signal to noise, right? It's always about increasing signal versus noise. So this is just an example of your matrix, right? Just remember, how do we figure out not how big a pixel is, but how many pixels we have is we multiply the two numbers. And not necessarily in MRI, but in X-ray and CAT scan, the sides of the pixel are all equal. So you have little squares, right? So you have a symmetric versus an asymmetric matrix, right? Asymmetric means you can have rectangles, but everything is nice and square in radiography and in CAT scan. So you want to know how many pixels you have, you just multiply 512 by 512. In this case, it's 262,000, so on. Okay, I have like one thing to say. Sampling frequency. So first of all, you don't want to undersample. Undersampling means you, so why are you sampling? You're trying to speed up the process of reconstruction. So if you undersample, you can get artifacts. And of course, that means signal to noise goes down. You want to sample enough so that that doesn't happen. that enough is governed by what we call the Nyquist theorem, right? And in the Nyquist theorem, you want to make sure that the frequency is at least, if not greater than twice the bandwidth of the signal that goes in. So another way to say this is you want to sample at least twice per cycle. I'm just trying to see if I have, no, you got to take a look at the rest of the presentation on this. So just so you know, a lot of this information has already come from presentations that you should have, right? So I will try to remember to send you the syllabi that I have for 1126 and 226 that has all the presentations on them if you don't have it. So that's something I'll send you guys. All right, the other way to know that you're doing a good job is to look at what's known as the modulation transfer function, or the MTF. So if you remember, the MTF comes from 3 or 4 different other tests to look at the efficiency of your system and how well you can potentially illustrate an object and compare that real life object to the projected image, right? The closer you get the real object to the projected image, the better, right? So MTF takes into account separate tests. There's an edge response function, there's the line spread function, there's the PSF, the point spread function, or SPF, like suntan lotion. The MTF takes those, doesn't just average them, I'm not sure how it's done, takes those other Q quality control tests that give you those numbers, puts them together in a certain way to give you your modulation transfer function. And the MTF goes from 0 to 1, which doesn't sound like a lot for a range. 0 being the worst possible image, the worst example of converting your actual object to the image object. And 1 is the best, which is also impossible. I should say also impossible. 1 is impossible. 0, if you get a black image, that's possible. You can get a 0. But the range actually goes by tenths of a point. So it goes 0, 0.1, 0.2, 0.3, etc. Right? So if you got like a 0.7 on your MTF, it would say, this is a good way to kind of define it, it would say that 70% of the object information has been transferred to the image. So you can't get a 1 because that would be 100%, right? That would be like exploratory surgery, where you take the object out and look at it, right? It's never going to be that good. But those numbers can get higher as the technology gets better.
Professor, can I ask a question regarding the modulation transfer? So you said you cannot get 100% of the image to the object. Could that be because you might get some magnification in the image that you wouldn't able to get?
Yeah, there's always, so it's not exactly well defined what that 30% is missing or why you only got 70% versus 30%. So it's not 100% clear, but it could be. There's always some slight divergence of the beam.
Okay.
So there's always going to be, a little bit of elongation, whether you angle the tube or not, just on the slight angle of the photons coming out of the tube. There's always going to be a little bit of OID, right? Mm-hmm. So there are little, things that are just inherent to the patient and the part that are not going to give you the exact dimensions and perfect object on the image. It's going to be close.
Yeah.
But it's never going to be perfect.
Okay.
I have a question with MTF. Is MTF directly correlated to contrast?
So
I always see a question with MTF, and the answer always somehow deals with contrast or like the level of contrast. but never really
Yeah,
spatial
it's
resolution. Like, you know, I'm
yeah,
always,
it's more related to contrast than it is spatial resolution. But in a way, it's when they say contrast, it's just trying to represent the object. And the level that X-rays can represent the object is limited. So not bones, but for instance, soft tissue. If you look at soft tissue, it's very low. So MRI would technically have a much higher MTF for your cruciate ligament than in your knee than an X-ray would, where you barely see it at all.
yeah, because
So
contrast could distinct basically a bone from tissue. You know, that's what the whole point of, you know, contrast. But not like
correct.
because spatial resolution is more of like a clear image. You can have a clear image, but like horrible contrast.
Right. So I think this is more of a contrast level of accuracy than it is a spatial resolution level. So I would agree with you there.
But it says spatial resolution right there.
Where?
At the bottom of that PowerPoint.
Yeah, it's kind of both, but yeah, I would, I'm tempted to change that. But so I mean, I'll give you a better definition. Let me. I know Catherine's keeping track. I've seen it in different books kind of describe it both ways. I usually talk about it under spatial resolution terms.
I recalled when you explained it to us, you said the MTF is actually trying to the image come as close as perfect to the object. So it's like the transfer, how you see the object, you want the image to be as close to it as possible. The information transfer.
And then, so what Zabir is saying and what we're talking about is, so based on what you just said, is that more contrast or is that more spatial resolution? I think that's
I would
the
say
question.
spatial resolution because if you want to able to see, as you said, the difference, like the edges. You want to see.
What I'm trying to say is sharpness, right? Does that figure out the object, or is that just like clarity? You know what I mean? But contrast shows exactly what the object is in shape, and it's distinct.
No.
That body
So
part.
it's like you can argue both. I think you can argue both sides of it, right? If the contrast is not good, then you can't tell it from an object that's, let's say, in close proximity to it.
Right.
But if the spatial resolution is not good, then you might not see it at all. So there's a good argument for both of them. That's why I'll do a little research and see. So I initially, this is under the spatial resolution part of your textbook. So that's kind of where they see it. But Zabir, did you see it elsewhere under contrast?
It's just every single question that I come across with MTF, the answer always deals with contrast.
Well, if that's the right answer, go with it. But so if you can send me one or two of those questions where the answer is contrast, I'd like to see what the other choices are. But either way, I wrote that down. So we'll take a look at that. Okay, let's keep going. So Nyquist, I think what you want to remember is at least you have to sample at least twice per cycle is the rule. And again, I have this another slide or two in the actual lecture when we went over this. So we were just talking about contrast resolution. That's being able to distinguish objects based on them having a different grayscale. One is darker or lighter than the other, and thus you can tell it's something different, right? Whether you know that it's the same object and it has pathology or not you know, might start to drift into spatial resolution. So what you want to do is you want a good amount of each, but I have found in many cases it's very hard to maximize contrast resolution and maximize spatial resolution at the same time, right? That's kind of the dilemma, right? I'll give you an example. We were just talking about pixels. If you have smaller pixels, your spatial resolution goes up. But if you have smaller pixels, your contrast resolution goes down. And your contrast resolution goes down because the associated voxel is also smaller. And the bigger the voxel, the more data and signal you can put into it, that improves your contrast resolution. So you can't have small and bigger pixels at the same time, right? So in any given image, at least based on pixel size, you're going to have a certain level of contrast and a certain level of spatial resolution, and you can't get them both to be at the highest level without one going down. So that's kind of the dilemma. The only thing that I know that can improve both contrast and spatial resolution is more data in general, right? So if you have more penetration and you have more data, or something like your fill factor were to increase, that would give you more data because less photons would die. That might potentially improve both contrast resolution and spatial resolution. But when it strictly comes to voxel size and pixel size, you can't get the best of both worlds.
Professor, could you go over voxel? What you said, if the voxel is smaller, you're going to have less contrast or more contrast? Because I would think you'd be more wide.
Okay, so the way it works is the pixel is the square. It's like the two-dimensional object. The voxel is a cube. It's like the three-dimensional object. But they are intertwined with each other. So if you take the cube and look at just one side of it, that's the pixel. So by the way, when you figure out how many pixels there are, it's the same number as how many voxels there are. Now, when you increase the pixel, you increase the voxel at the same time. If you decrease it, then the voxel, the sugar cube, gets smaller. So when it comes to pouring in signal, a bigger bucket, a bigger voxel will give you better contrast, higher signal to noise ratio. When you reduce the pixel, the voxel gets smaller. That means signal to noise ratio goes down and contrast goes down. So if you're making the pixel bigger or making the pixel smaller, it's going to affect one of them positively and one of them negatively. When I say one of them, I mean contrast versus spatial.
So if the pixel is smaller, you get better spatial resolution, but the contrast is lower because you get more black and white. Because that's what you would get. Then
it's just less. I wouldn't say black and white, but I would just say less signal.
That's grayscales.
It relates to grayscales, yeah.
Yeah, but the smaller one would give you less grayscale, but higher spatial resolution, whereas a bigger voxel would give you less spatial resolution, but more grayscales or longer grayscales. So
yeah, so a bigger voxel, meaning a bigger pixel, means you might not be able to resolve smaller objects.
Exactly.
Okay, so your spatial resolution goes down.
Okay. Yeah.
Yeah, so that's a big factor in MRI and CAT scan. Not so much in thanks, Michael. Not so much in X-ray, because essentially each radiograph is a giant voxel. I mean, when you do an abdomen, you're going from the front of your body to the entire back. You're not slicing anything in any which way. So in X-ray, regular X-ray, we're not talking about slice thickness. In MRI and CAT scan, how thick the slice is makes a big difference. And that's where the voxel really comes into play. So I don't know how deep they're going to go on this. I probably go deeper than you need to know. You know, I don't know what kind of questions you're getting related to voxels versus pixels. Hopefully they're not too crazy. Okay, speed class. So this is an old term, and it still relates to CR the way it did relate to film. In DR, I think there's still a slight relationship, but not that much. Take a look at one of those links that I sent you at the very beginning. So guys, whoever came in late, go back to the chat at the very beginning. I put like 4 or 5 different links that you should copy and put someplace, and put in a Word document or whatever. And those will give you some more information. But one of those links is related to an updated digital, and anything that's in there doesn't include CT. So if speed class is in there, then you definitely need to go through.
Professor LaBelle, would you mind emailing those links? I mean, I copied them, but if you just send the reporting along with the links, because after the chat closes, they will disappear. Would you
Yes,
mind?
is this
Trouble?
Natalia?
Yes, this is Natalia. Yeah. This is
how did your lecture go? Your presentation?
Oh, wonderful, wonderful. I was able to make it, and they
good.
went over time. So the director of CRSP program, Ron Nerio, he said, well, you know, we went overboard. So my presentation was very nice. It was in time limits, and people asked a lot of questions, actually. I didn't expect so many.
Oh, good. So I'm going to, out you a little bit here. Thank you, Natalia, for representing our department today in the research
college,
studies.
the entire college.
And represent the entire college. So, we should all appreciate your work today. So thank you for doing that.
Thank you. I appreciate it.
Okay. Oh, yes. So what I will do is, before I end, I'll stay on for another couple minutes, and I'll make sure that I copy my own links so I can email them all to you. Okay, so where are we? Wow, time is flying. All right, so speed class originally was based more on film, and the idea was that the higher the speed class was, the lower the exposure you could use. So it had to do with the sensitivity of a film chemical-based system. That was then kind of translated and moved on to CR. So it becomes even less relevant, really. The idea, once upon a time, is that a standard speed used to be set at 100. This was an arbitrary term that the powers that be came up with. And they said that if you had a speed film of 100, it would correspond to 2 MR of radiation. And that in turn would give you a density reading, so the blackening on a film of 2.5. Now, what that would mean is that if you went to a 200 speed, then your ability to get an image would be cut down to 1 MR. So as the speed doubled, the amount of radiation needed to create the same density would go down, right? So I think the way you want to think of this is, the higher the speed, the less radiation that you need. However, what you want to keep in mind is, if you set the speed higher, your likelihood of getting noise is higher. So remember the golden rule, the physics haven't changed. If you don't have enough photons and you don't have enough intensity, it results in noise. So in terms of dose, when the speed class goes up, you can use less radiation. That will reduce the dose to the patient. However, your image can be a little bit noisier. So here's the example, right? if you go to 400 speed, notice it went down from 2 to 1 and halved again. So it keeps halving as the speed goes up. I think this is more of a CR thing, and I don't even know if I have to talk about this in the future. It was going away already, just for you guys. So the bit depth is how many grays any given pixel can display. So remember, the bit depth is 2 to the power of the bit depth. So if you get a question that says the bit depth of this system is 8, how many grayscales can a pixel demonstrate? It would be 2 to the 8th power, right? So 2 times 2 times 2, etc. 2 to the 8th power would be 256 shades of gray, which is not a lot, right? It might be more than we can actually see physically, right? We talked about that in class, how we are limited, as physical human beings. But this thing commonly goes up well over 1,000 different shades of gray as the bit depth increases. So here's MTF again. So if you can see here, right, just based on this definition, we're looking at alternating signals in the X-ray beam, the remnant beam, alternating densities / brightness levels. So Zabir, to your comment about it being more contrast resolution than spatial resolution, it's tough because at the end of the day, all you have is pixels. And all you have is those individual pixels giving you a particular brightness level for each one. So, contrast resolution and spatial resolution are sometimes a little bit tied together because at the end of the day, it just comes down to various pixels and their brightness levels, right?
I'm on Clover right now, and I was answering a few questions, right? And then it was saying how MTF is inversely proportionate to spatial frequency.
MTF is inversely to spatial frequency. So that's saying if the MTF goes up, spatial frequency goes down?
So when spatial frequency is very small, that means the modulation transfer function is getting better.
Oh, so that would go with the definition he just said, right? Spatial frequency going down means MTF going up. Is that what you just said, Natalia?
Yes, I believe the concept is that when the spatial frequency is small, it creates a better modulation transfer function.
Yeah, like 1.0 MTF is gonna be with 8 LPM, which is gonna give you the best spatial frequency.
Yeah, so that sounds more like spatial resolution than contrast resolution. So I that's why I see MTF kind of holds the line between the two terms. But yeah, so I'm okay with that. With what Clover is saying, MTF is inversely proportional to spatial frequency, which kind of makes sense. Now, detector quantum efficiency is similar in that it's prior to the pixels, right? Thanks, Raphael. Where's that coming from? That you copied it from?
Yeah, that was from AI, but specifically it says I don't know, cloudy nights +4. I don't know what reference that is.
I have
Oh,
another.
sorry, that's a different one.
So I have
Okay.
another thing that is confusing because LP over millimeters is how you measure spatial frequency, right?
Line pairs per millimeter, yeah.
Yeah, so it's saying the lower the line pairs, the higher the MTF score. Does that make sense? Because it's saying 1 LP compared to 9 LP over MM has a higher MTF score.
Okay, hold on. So 1
So
line pair per millimeter versus 0.9 or 9?
Oh, 9.
So 9 line pairs per millimeter is very small. That should give you much better spatial resolution.
That's what I'm saying, but it's saying it's a lower MTF, so that means MTF is inversely proportionate to spatial resolution. Then,
Where did you get that? Because the more line pairs you could recognize without any blur, that's better spatial resolution.
It's a spatial frequency or spatial resolution.
This is spatial frequency. A lower spatial this is what it says when it says feedback. It says a lower spatial frequency has fewer line pairs per millimeter. At 1 LP over mm, the modulation transfer function MTF score is a 1, which is equal to 100% and is ideal. As spatial frequency increases, there are more line pairs per millimeter and image fidelity or MTF decreases.
Okay,
Okay,
so
you're saying, yeah, okay.
what I'm going to do is I'm going to put together a couple bullet points and a couple of paragraphs or a paragraph on spatial frequency versus MTF versus spatial resolution versus contrast. So I'm going to put down, I'll do a little homework. I'll put together something that I hope will be understandable, and I'll send that to everyone.
Yes, CBR, I understand what you're saying, yeah.
And I'll, define spatial frequency versus, line pairs. Okay. So we are at about our time. So let me show you where we are. So, whoops, let me share that for a second. So we are at, we had lots of questions and discussion today. So we got about halfway. So we are at slide 75, and there are some basic things in here that are not hard, but this goes to at least 170 or so, 177. So I will do the rest of this in the next day or two. I have a class actually that starts at 6, or else I would do it today. So give me a couple days to put some of this stuff together. And I will kind of continue this. And then if we have some and I'll put together the MTF versus spatial frequency, et cetera, that I just mentioned. But what I want to do now, briefly, so you guys don't have to hang out, but I just want to make sure that I get it all, is I just want to open up a document in so that I can put the links. So let me just create a blank document. So anyone that needs to go can go. I just want to make sure I get this done before I turn the thing off, because like Natalia said, you lose the chat. Although I think I get a log of the chat, but maybe you don't get it. So hold on just a second. Registry review links. Okay, so where are all my links? Hold on, guys. Yeah, my stuff is crazy, if you haven't figured that out. Where am I? Okay. Anyone have a specific question? I'm just doing some cutting and pasting. So
is DQE and MTF directly correlated?
I think
I
DQE has
would
to
probably
the
go
flat
ahead.
panel detector stuff. And like that's a whole different other topic with DQE.
No, because in Clover, it's every single topic that deals with MTF, its feedback always comes back and mentions DQE as a correlator.
It sounds like they call it.
Because remember,
Because
the Q is quantum, so that's the amount of photon reaching the receptor. So I guess the transfer isn't something like that.
well, the question is there a relationship between DQE, detector quantum efficiency, which is how well essentially detectors respond to
Photon.
various photon energy levels.
Exactly. So
And if the detector quantum efficiency goes down, I would expect everything to go down.
yeah.
But Sabir, you're getting a lot of this stuff from Clovers,
Clover, yeah.
from Clover,
Rad Bootcamp.
Rad Bootcamp. That's a different company, right? Look into that. Rad.
No, it's the same. But they just have the Rad Bootcamp. It's the same Clover, but they just have a new thing called the Bootcamp, prepping you for the.
Oh, okay. Okay, Rad Bootcamp is Clover. Okay. Yeah, I think. Oh, okay. I have just a couple more. Wow, I gave you guys a lot of links. Okay, I think I got everything for you. Okay, everyone. So I'm going to end things there. I'm going to send you more stuff. I'm going to record the rest. So the other 75, 85 slides, send that out to you. So look out for some emails from me. And if you guys want to send me a couple of questions, especially about DQE and spatial frequency and MTF, I'd like to see those.
Professor, you're going to make a video for the slide you were working on, right?
So I've already videoed everything we've done to this point, and then I'm going to video just the rest of it, except I won't have a live audience, but I'll send the rest of it to you all. Yeah.
Since that's going to take time, can you send the actual slides before that too?
Well, yes, the slides are done. The
yeah.
link, yeah, that was one of the links I gave you at the very beginning. As a matter of fact, it's like the only one I titled, the last one. It says 2026 image eval review.
Oh, nice. Because I did come in a little later because I was on the other Zoom.
Okay, so I will put it in. I'll re-put it in the chat right now. One second. Let me just re-paste it in.
Professor, can I ask a question?
Sure.
So the PowerPoint slides you're going to upload from this section that you're doing, is it encompassing your first and second class, or should we still go through your syllabi for the first and second class?
Okay, so the link that I just sent just now, that's all the slides, even though we didn't go over them all today.
Thank you, Professor.
So,
I got it. Thank you.
Yeah. So that's all of the slides, right?
Okay.
But we got we had a lively discussion, so that's good in a way.
Listen, we missed you, Professor. It was fine.
So some classes, no one talks at all, and I just zip through almost every slide. And then other classes ask, and I think you guys are doing the right thing because you're getting questions from questions, right? Which is kind of what I started with in terms of how I think you can pass better. My stuff tends to be a little bit confusing. because like I was saying, it all ends up being pixels at the end of the day, right? Various pixels. I mean, you magnify an image, it's just pixels. It's still the same number of pixels. They just have different grayscales that duplicate the few grayscales that were next to them to make things look like they're magnified, for example. So, everything ends up being, your pixels. But in order for your pixels to get good information and accurate grayscales, that's where your detectors, some detectors are better at collecting data, and the more data that you have, the better your image is going to be, right? So DQE is very important, right? It doesn't matter how, large your matrix size is, for example. All right, everyone. I could keep going and going and going, but I need to give myself a little break before I have this little review tonight.
It was nice to see you again, Professor. Thank you.
It was nice to lecture again. So I will see you all soon for sure. But I'll definitely be in touch via email. And if I don't speak with people directly, at the very least, I want to know that you all passed. So, definitely send me a yay, I passed. I did hear from a student like a year ago, and she did very well on my particular section. So I was very happy about that. So that was nice. So thank you, everyone. And I will be in touch. If you have any questions, just email. And like I said, I have a few things to put together. So give me a couple of days and I'll get this all to you. So
Professor.
Thank you, everyone.
Have a nice summer, Professor.
Thank you, Professor LaBelle.
I plan on it. I'll talk to you all soon.
Professor LaBelle, just a question. Are you going to be uploading this recording as well as the presentations, or just the presentation?
Yes, I'm going to upload this recording, and then I'm going to upload the second recording, which will be the rest of the slides that I'm going to do, within the next couple of days.
Perfect. Thank you so much, Professor. I appreciate it.
Thank you, Professor. Bye.
Bye, everyone.
Mobilize.
There you got it.
Mobilize.